immense pleasure to introduce Maxim Kontsevich, a great scientist, mathematician, physicist, and even better volleyball player, who's going to tell us about variational invariants from quantum cohomology.
Okay, thank you. Yeah. So this quantum cohomology or Gromov-Witten invariance appeared 20 some years ago, almost 30 years ago, and it was kind of explosion in algebraic geometry. But they say that you can count now how many curves of degree n, rational curves, pass through Cn minus 1 points on CP2. Nice genetic functions, okay, but it's not really central equation of algebraic geometry, I have to say. Yeah, so it was kind of part of, say, symplectic topology, algebraic geometry, but without any use in algebraic geometry in proper sense. But now I'll try to say that it's kind of a very recent project which started about months ago, maybe with Lidmila and Tony, which should have been done 20 years ago, and application to birational geometry. So from all this Gromov-Witten theory, we need only genus zero part, GV invariance. And it gives us Frobenius manifolds and blah, blah, blah. And then we get applications to algebraic geometry. Not new, just that applications here, because there's no applications before. Let's say, strictly speaking. So we'll have birational invariance. And let's have a variety of complex numbers. For example, I will demonstrate how using these things we can prove that generic cubic fourfold is not rational, which is very old open question, but our invariant seems to be so strong that it could be kind of kill the subject in senses for any variety. Immediately we can say. Second, it will interact with Matevich-Galois group in some interesting way. Yeah, for example, one can make the generalized birational invariance for non-algebraically closed fields. Also, one get new functionals on K0 of variety. You just cut and paste variety over some field. And it's something much finer than K0 of motives. One can sometimes people analyze through K0 of non-commutative varieties of saturated categories. But in the saturated categories, for example, abelian variety and dual abelian variety became identified. And here the different, which is hard result, and in this approach it will be immediate, the distinctness, and also will be something maybe kind of about canonical singularities and how to deal with them. And also in relation with minimal model program. Okay. So what's the point? It's extremely easy. Maybe I'll formulate the first in symplectic language. Suppose we given a compact C-infinity manifold of even dimension, then we can see the set of all symplectic structures. That means it's two forms which are closed and non-degenerate at any point. So it's infinite dimensional manifold. We take connected component. Pick a point in pi 0 of this guy. So it's not really symplectic structure, not even class of symplectic structure, but still it gives you some rough information. When you consider the symplectic structure up to deformation, it gives you a reduction of structure group of the tangent bundle, which was originally GL to NR, homotopy equivalent to orthogonal group, is reduced to symplectic group, or the same as unitary group, homotopically. And so one can speak about chain classes. Before we can speak only Pantragian classes, but now we can speak about chain classes. And with chain classes, one can define some non-symmetric, not anti-symmetric pairing on cohomology. Let's say with rational coefficients, say. And it will be integral on image of topological K-Curie modular torsion in rational cohomology. And the pairing is the following one. Like imagine your manifold is actually Keller manifold. And you have two, say, even classes, and which are chain classes of some bundle. So what the pairing between chain classes of E, classes of F, and pairing denoted by Euler pairing, it will be Euler characteristic of R home from E to F if everything is complex analytic. And in general, what one can do, one consider index of Dirac operator d bar plus d bar star, adding of sections of X E star tensor F and multiply by even d bar forms for some almost complex structure to the same thing with odd d bar forms. Okay, so there is a theoretic definition, I get integer number. Okay, so I get this pairing, and which play crucial role, this Euler pairing, which now kind of a very general thing. If we have V some vector space over some field, finite dimensional, maybe super vector space, as we have cohomology as Z2 graded space, and we have some non-degenerate pairing, not symmetric, not skew symmetric. So AB is not equal to plus minus BA in general. Then one can consider semi-orthogonal decompositions of certain lengths L. It's just a sequence of subspaces such that direct sum of VI's is isomorphic to V, so it's decomposition direct sum, and scalar product of, let's say, VI with J is 0 for I greater than J. And this means that if you choose a basis of your thing compatible with things, this pairing will be given by block upper triangular matrix. And on the space of such, on the space of semi-orthogonal decompositions of length D, L, this action of braid group. You just consider these things will be non-degenerate on each block because I assume the whole thing is non-degenerate, and then make left and right orthogonals, you get braid group action. Okay. And in our case, of course, we will be cohomology of XQ with Euler pairing.
So the braid group is some kind of reflection operator?
Yeah, just for if you have a subspace, you can yeah, I can exchange, put a plus 1 on order of I, and there will be unique choice of I plus 1 next step. Yeah. Yeah, so I get these things, and the claim is that this, or maybe here, this symplectic structure up to deformation which is kind of discrete choice here. Sorry? E, F will be complex vector bundles. Yeah, but it's explained by linearity because modular torsion, it's K-Turing cohomology coincide up to torsion. On, yeah, it's even and odd, so you ask about. With rational coefficients, because with rational coefficients, just linear span. Yeah. Yeah, if you have symplectic structure up to deformation, the claim you get canonical first number L depending on X and this kind of like complex structure, which are called lengths of my symplectic manifold, which is invariant and deformation complex structure, and so it will be bigger than 1, and canonical, also canonical BL orbit in semi-orthogonal space of semi-orthogonal decompositions. Of cohomology of X, yeah. Over, but really important things. Here, at this point, we can say of cohomology with complex coefficients. Yeah, I should be very careful. Here, the field is complex numbers naturally, nothing else. And conjecturally rational, yeah, but I kind of construction gives over complex numbers. Let's discuss the construction. So how we'll proceed? So I recalled this quantum product. I've used this conference. I suppose you know what is quantum product on cohomology of X. Yeah. So there are some traditions in the subject, very old traditions. Says, like, choose a basis first, a graded basis of cohomology of basis I denote by delta I, and I choose basis only of even cohomology of X with rational coefficients.
Quantum product means small quantum product?
Small quantum product, yeah. Actually, it will be smaller than small. It will be because I multiply only by even elements. Yeah. So the basis will be the following. The first zeroth element will be 1, which is belong to H0 xz, which is yeah. Then you get up to second Betti numbers will be elements of H2. Here should move out by torsion. And I assume that they form they span a cone which lies entirely in this possible classes of symplectic form. Assume that omega I, delta I from I1 to B2 is class of some symplectic form in our connected component, and all positive linear combinations are also symplectic. if you get one symplectic form, it's very easy to make this sum. And I assume that this kind of this, maybe this form basis. Always you, all Q is enough also. And then other guys. Yes, yeah. It's a very easy exercise. Okay, but basis over Q it's even simpler. Yeah, okay. And deck of dg is greater than 4 for g bigger than b2, which is rank of h2. Yeah, so I get this variables, and we kind of deform usual product by kind of sum all by this cohomology class, and these things we do in the limit. You can see the limit when components corresponding to second cohomology go to minus infinity. And this B2 variables we replace by Qi, which is exponent by Ti. Which will be numbers which goes to 0. And quantum product it will be kind of map Qt from cohomology of X Q, cohomology of XQ, cohomology of XQ multiplied by a ring of form power series in Qi from 1 to B2 and Uj with J bigger than B2. And there's no dependence on T0. Quantum product doesn't depend on T0. Sorry?
J is bigger
than B2. Yeah, so I get product, and now maybe I go to the blackboard. There are two operators on cohomology of X, and now I put this coefficients ring Q and T, but now including T0, T and Tj, the degree of Dj is greater. So I now include this dummy variable T0. And one is operator, I thought how to denote it. Just for this lecture, I choose letter K, explain in a minute why. It's the following thing. We consider the following element. We consider canonical class, which is C1 of cotangent bundle, and plus small correction. Correction appears when we in deformation put some classes of degree not 2. So we have not only variables Q, then will be certain correction, but it's very tiny one. So it's sum over I, J such that degree of Dj is not equal to 2. So it means that T0 or cohomology on degree 4 or bigger, then one have something like 1 of degree Dj minus 2 times Tj times delta J. And we use quantum product, this Qt. Yeah, so it gets some operator from, I call it roughly denoted by H, from H to itself. I get finite dimensional free module over this ring and get endomorphism K. So it's, one can say it's quantum multiplication by canonical class plus some correction. And maybe plus corrections. And you see that it's in this words, it starts with K, yeah? But it's written in different, in Latin, yeah, alphabet. And in Russian alphabet, if you're in Moscow, I can write it's квантовое умножение на канонический класс с коррекцией. Okay. And this now it starts with letter k many times. Yeah, so it's better denoted by k. Yeah, so it will be Cyrillic k. Yeah, so it's just okay. Sorry. And another operator G will be a pretty stupid one. It's just something which measures the grading in. We consider I minus n over 2 times identity map of. So it's rescaling grading. Yeah, this is semi-simple operator with spectrum in half integers. And the first one is kind of T0 minus 0 times the identity operator plus deformation, small deformation of nilpotent operator multiplication of TZ plus deformation of nilpotent. Yeah, so there are two very different nature. And it's kind of was known from the very early days of this Gromov-Witten theory that scaling grading properties of multiplication gives the following. You have irregular D module on a affine line minus 0 with coordinate called u, which is kind of trivial vector bundle. And connection is given by du plus u inverse k plus u minus 2k in u inverse g. This is irregular connection, and we get isomonodromic family when we change parameters q and t. You get.
So this line is over this spectrum.
Yes, it's a fine line over the spectrum of this ring. Yeah. It's you get isomonodromic deformation over this variables q and t, but q should be non-zero. I think it's when q is equal to 0, it's kind of singular limit for the connection. Sorry, k is not nilpotent. It's deformation of nilpotent because it's if classical product is. I think it adds some kind of small corrections. Yeah.
The quantum product of C1 is non-zero, right?
Sorry? Yeah, it's good.
The product of C1 is not important.
Sometimes. Yeah. Like for Calabi-Yau, it's nilpotent. Yeah. And but then one can do stupid things. One can go to inverse variable, make Fourier transform, or one can equivalently to say make from this holonomic D module now over a affine line without 0, and somehow the variable on this affine line is the same variable u, but it's not something which contains. It's kind of accidentally. This has the same scaling of degree plus 2, and now you write. It's not. It will be no longer bundle, no longer vector bundle with connection. It's kind of Fourier transform of the thing. It's a certain D module, but it coincides with some bundle of this connection outside subset of spectrum of operator k, which sits in a affine line, and here you should solve different differential equations. It's maybe minus plus k du plus g. We try to solve such differential equation. It's up to applying Fourier transform. We get the same story, and we get isomonodromic deformation of this thing. Sorry? Yes, minus u over d, minus u du du plus k du du plus g. Yeah. And there is some duality properties. K transpose is equal to k and G transpose is equal to minus G when you use Poincare pairing, not for Euler pairing here yet. Yeah, so it's something about two matrices depending on small parameters. What? It doesn't depend on choice of a basis. This basis is a right. What is your problem? No, I don't understand. Operator, no. Operator depends on variables q and t. Okay, but it's k maybe depending on q and t. And so from very beginning we choose a basis, and if you want to formulate it in a variant way, you are welcome. See, just it's, no. What does it mean? You have classes and maybe in second homology and classes. Yeah. So it's okay. Yeah. Okay. Yeah.
Why did you get a first order equation?
Yeah, no, first you just, maybe you consider inverse variable for u here, v. You get d module again on a fine line on inverse variable, and then make Fourier transform. And then if you make Fourier transform, get certain d module, and if you look on it, you just replace operator by.
I'm worried more about the square than the inverse. So the fact that
you multiply maybe u squared, yeah. You multiply things by u squared.
Right.
And
I was just worried about the square, not about the inverse.
You go to inverse variable, yeah, okay. At the end of the day, it's very old theory. It's I think in our paper is one, and we also wrote it. Dubrovin wrote it. Yes, it's kind of.
I think the question is, why is that not d squared d u squared?
Because it's actually an inverse variable. Because if you go to inverse variable multiplied by u squared, it will be d over dv. Yeah, maybe just make some little calculation here. You just write these things, yeah, plus k plus ug. Then replace u is equal to v inverse, so we get something like du dv. Second, plus k plus v inverse g, yeah. Then multiply by v. Now replace v by du du. Okay. Yeah, it's little calculation like this. Okay. Now what? So we get two matrices in form of our series, and I kind of can assume T0 equal to 0 because it just shifts by constant. It makes no sense. But so I get matrix very, very close to 0, another is constant, and assume kind of for a moment that series convergent for small q and t. Which should be the case in real life. We don't have a proof, so but if one want to write kind of formal proof, it's based on proven assumptions. Yeah. So assume that convergence, then we can substitute complex numbers and get spectrum of k, which in C, which is finite subset. And it depends analytically on this variables q and t. So it means that it for open dense subset, it has the same number of elements, and then in complex hypersurface it will they will merge together. So L of x will be defined as number of kind of distinct eigenvalues of k, qt, or kind of cardinality of the set spec qt for generic q and t. Yeah, so it's a well-defined number. Now, let us choose collection of paths from minus infinity, disjoint paths, minus infinity to elements of my eigenvalues. So I get eigenvalue lambda 1 and lambda 2. It will be lambda L. So you get this disjoint path. It's something sometimes called Gabrielov basis. So for fixed Q and T generic, fixed generic QT, and choose a Gabrielov basis. The Gabrielov basis is not unique. It's a torsor of a braid group. And it's well known for these differential equations, so it's very well studied, that if you get such a thing, then you get, with this duality for pairing, then you get semi-orthogonal decomposition, now for Euler form, of your space. And pieces correspond to eigenvalues, and if you apply braid group action on this collection of paths, you get braid regression on semi-orthogonal decompositions. Yeah, so this will be the invariant. Because if you go from one Q and T to another Q T, you just can by continuity identify such things. Yeah, so here there is some fine point I will discuss in a second. Yeah, I say here Euler form, and before it was Poincare pairing, and in the formula for difference you get also some Chern classes, but in identification with cohomology, we should use gamma class, which observe square root of third class, and then we get essentially first Chern class, which measures difference between Euler pairing and Poincare pairing after this. And that class will play the role. Okay. So now.
I'm a little bit confused about something. Why is it that if you can you explain how you get this set of power?
Yeah, I'm explaining in some way. It will be some in a couple of minutes. I'll explain. Yeah. Yeah. So maybe right now, I'll just go to some. No, just a second. I'll explain it in a second. But first, I want to say what to do without assumption on convergence. What should one do? One introduce, instead of complex numbers, introduce Novikov field, which is just series in some dummy variable, capital T with real exponents. It's algebraically closed field. And put Q and T elements of the Novikov field of non-Archimedean norm strictly less than 1. So it means static with some positive power of t. Yeah, so on, then it's perfectly, series will be all convergent, and you get matrices K, Qt, and it will be operator defined over this Novikov field, and G as well. So you get actual things. And what is the spectrum of K? So it's subset of my Novikov field. Again, generically will consist of L distinct points. And now I have subset of non-Archimedean field. And that's automatically, they form I consider like diameter of this subset, and measure things up to this precision given the diameter. Then for each block, when you don't distinguish on this distance, you measure from smaller things, and you get a tree. You get automatically for any subset of non-Archimedean field, you get such a tree with L leaves, and on each vertex at each vertex you get polynomial of a complex numbers with distinct roots. And maybe one can normalize with sum equal to 1 for each vertex. You get again finite subset maybe of C, defined up to shifts, and positive rescaling. And positive, and what you try to think, it's try to think that T is a variable which is real and positive, but very, very small. So it will be a relative position of roots on next level of precision. And so, what you get? You consider, for example, this leading term. This your roots decompose, let's say, on some 3 groups. And then for each group, then for this one is decomposed like from another 2 groups. So you get another 2 elements. And then what really happens if you choose Gabrielov basis here and choose Gabrielov basis here, you kind of can substitute smaller version of these things inside, and you get Gabrielov basis eventually of the whole story. So that's choices of Gabrielov basis for each subset in C gives some kind of specific class of Gabrielov basis in over the whole family.
So the braid group gets replaced by some process.
Yeah, it will be kind of, it will be certain subset of the torsor of a braid group of L. You get a subset of a non-empty subset of a torsor over BL. It will be, by this picture, you get not arbitrary ways to connect the whole things to infinity, just it's compatible with. Yeah. Yeah, so one can still make kind of, even in non-Archimedean case, one can choose some kind of Gabrielov basis, maybe not the whole or BL orbit, and then that gives again semi-orthogonal decomposition. Now there is a question how really can make the semi-orthogonal decomposition, and there is also point which I explained in a moment. All cohomology. You get splitting of all cohomology, yeah, because it will be both in even and odd separately, yeah. Also split in some part, yeah, sure. Yeah, so this is kind of very fine analytic point. Yeah, when consider this differential operator outside of on C minus spectrum of K, let's imagine our complex numbers. This operator typically has regular singularities, but sometimes has not regular singularities. So it's, has regular singularities in it's when it has regular singularity, it's kind of Zariski constructible set in pairs of matrices. Not open, not closed, and it's true even in our constraint when G is semi-simple. Consider part where G is semi-simple with spectrum belongs to half integers, like given kind of diagonal matrix. It's still not Zariski open and closed. And how one can, the whole story was kind of analyzed when this thing is regular. It's kind of some assumption which we believe, but even without this assumption, one can survive. Without it, one can use some Dobson-Kashivara thing, which for irregular holonomic demodule, you can still make a perverse sheaf. Usually people know that regular holonomic demodules are equivalent to perverse sheaves. It's not equivalent. It's just kind of like forgetting some information. You get regularization of your regular model. And I don't want to explain what is it, but here it's finally, what are these elementary pieces I want to say. No. Stokes matrices, it's equivalent to Stokes matrices if it's regular singularities. But if it's irregular singularities, then get more complicated Stokes structure. Now, if it's not regular singular, if I don't assume that it has irregular singularities, the property, the set of pairs of matrices when it has regular singularity, it's not the Zariski open and closed property that I will discuss. And without this property, G and K, you consider pairs of matrices, and we have differential operator, yeah? And sometimes it's regular, sometimes not. And it's kind of pretty nasty constraint. But even the regular one can construct perverse sheaves, but technically we need to just decomposition direct sum. What you should do, you consider a disk in C and a point on the disk. And assume the boundary of disk doesn't intersect with the spectrum, no singularities of equation lies on the boundary of the disk. If I have disk and a point, then I can associate a certain vector space, graded vector space, consider cohomology of the RAM cohomology in analytic sense of disk relative to point with coefficients in D module, which I didn't describe you explicitly by this thing. It's Fourier transform, my holonomic D module, say. And what I get a well-defined vector space. So I get this cohomology of pair. Now I consider disks containing all surrounding each marked point, connect by paths, and then direct sum. Sorry?
What is this point on the boundary? You think that
why is the point to the boundary?
you choose point on the boundary.
Choose some point on the boundary, yeah, and take cohomology of pair. Yeah, one can consider without point, but I prefer with, so it will be cohomology of pair. And what happens if you contain this part? Then it will be identified with this cohomology of big disk with one point on the boundary. This will be direct sum decomposition, and the cohomology of whole things relative to points of the boundary will be identified with the fiber of my bundle at this point, because for this D model, global de Rham cohomology is 0. and because it was multiplication by u, which was invertible, then du dx will be invertible. So this D module has is R gamma equal to 0. Yeah, so that's the definition. Okay, now we have this invariant. I explain everything. Now yeah, so there are some properties which prove something which cannot prove, so the kind of conjectural properties. Of canonical semi-orthogonal decomposition of cohomology. Yeah, so shows that this thing is D module has regular singularities. I think it's important thing, but one can survive without it. Just explain. Then, second is SOD is defined over rational numbers, and again via gamma class identification, and it's even integral if we use image of topological case theory up to torsion. So it will be really direct sum decomposition of the thing. But now it's more interesting. Suppose X is scalar. And use for deformation, I use deformation only along PP classes in even cohomology. Yeah, so it's a certain subspace, but it's contained ample class, so we can, for any such subspace, we can define the same property, and spectrum could be smaller for subspace. And then the conjecture is that its terms, SOD terms, have Hodge structures. Without base, it's kind of like non-commutative Hodge structures. We can consider only P minus Q filtrations. Okay, similar story if X is algebraic over some field in C, and use deformation only along what? You consider algebraic case theory of X. You consider image of algebraic case theory in, let's say, the RAM cohomology of X, even, and multiply by C. Then terms of SOD are motifs over K. Like show motifs, deramerization, stuff like this. And more optimistically, one considers SOD for X over K, SOD in cohomology leads to semi-orthogonal decomposition of derived category. Sorry? Sorry? Up to braid action. In shifts, yeah. No, but for semi-orthogonal decomposition, shifts are irrelevant. Just braid group action, yeah. And the size of braid group depends on this dimension of space in which you deform. It could be bigger.
So those conjectures you assume convergence?
No, without convergence, because I said that to have these complex numbers in monodromy, you need to go to this asymptotic analysis step by step, and you still kind of define.
Yeah, but then the cohomology is over not complete.
Because we have isomonodromy deformation, so we can go to the representation monodromy doesn't depend on the choice of your point. This representation, it's kind of the same. Yes, stays the same.
But what is this length in this mean?
You consider the number of distinct eigenvalues of an Noether field.
But an arbitrary precision or?
Arbitrary precision, yeah. And because it's so you have something like, and then they will be distinguished by finitely many steps in their precision.
So you can decompose the cohomology complex numbers using your bank.
Yeah, because you use isomandromy deformation, go to classical limit. All this decomposition can be transferred to the classical limit. Yeah. Okay, but what is now the main fun here? It's behavior under blowups, which makes the whole thing works. It's kind of additivity under blowups. That's key to applications. Now, so it's, imagine that X it's a symplectic manifold, contains symplectic submanifold. Then you can make new guy, just put some complex structure, almost complex structure, make formal. Sorry? So, oh yeah, thank you. Get blob, and this blob contains exceptional divisor. Yeah, assume that codimension of y is too small n. So you get exceptional divisor. This projects to x, and this projects to y with fiber Cpn minus 1. Exceptional divisor. And then you have the following thing: homology of x tilde. Sorry? No, it was symplectic manifold, but it put almost complex structure, say. Yeah. And one can make the same construction in symplectic geometry. Yes, exactly. Yeah. Yeah, so this cohomology of manifolds can be identified with direct sum as Z-graded space. Cohomology of x plus cohomology of y shifted by 2 plus shifted by minus 2 and minus 1, 2 and minus 1 as Z-graded space. And namely, you take here pullback of cohomology. You take this is denoted by J embedding J low star of P y cohomology of y, and then you start to multiply by delta 2, maybe n minus 2 multiplied by E star cohomology of y. So you get natural maps, and it will be isomorphism or direct sum. And claim is
Delta is the hyperplane function.
sorry?
Delta is hyperplane.
Delta is, oh yeah, sorry. Delta is, it's kind of a relative, you get line bundle, ample on each fiber. Delta is kind of C1 or kind of O1 for relative bundle, d over y. So the claim is length of x tilde is length of x plus n minus 1 length of y. And there is a similar statement. L of d is n L of y. Yeah. These things, I don't understand. It's either proven or almost proven, or should be proven by Li Lin in one It was a recent review, but people work on it for a long time, and it was Yingbin Ruan had some works in this direction. And so this is called this is called quantum Leray-Hirsch stuff.
Maybe I missed something. L in
Sorry?
what was L?
Length, number of distinct eigenvalues for generic quantum product. Yeah, it's some integer number, how many pieces you decompose, size of braid group. Yeah.
And you don't think there could be some disaster where it just so happens Y has all the same eigenvalues as X does?
It's okay, sir. No. Hold on. Yeah, I'll just explain you what's going on. And corollary that L of x tilde minus L of d is equal to L of x minus L of y. You get this property. And notice that x tilde minus d is equal to x minus y as constructible set. And this is generates relations of Bittner generates a relation of K0 of variety. So it means that length gives you a function of K0 of varieties. Okay.
Can I ask a version of the next question? So the symplectic form on Y is not canonically determined.
It's not canonical, but I don't need symplectic form. I need class of pi 0 of no concrete symplectic form play any role. Yeah, that's the things. Let's me explain. Sorry?
You see that this class is quite canonical?
What?
If you restrict the class of your symplectic form on x to y, does the class of the restriction?
No, a class first I fix symplectic form on x, has symplectic form y, and then I give elements of pi 0 of x, pi 0 of y, and also gives me elements of pi 0 of space of symplectic form of blow up.
This thing is a symplectic submanifold for specific symplectic
For some
form.
for any specific, I choose any specific
So
symplectic.
there must be some kind of relative.
Yeah, no, for example, I choose symplectic form on x and such that y is symplectic submanifold.
Okay.
Yeah.
That's already pi 0,
No.
some other space. Not
And then we get pi 0, that elements of pi 0 of the space of symplectic forms on x and y. Yeah. Yeah, in this situation, when I have concrete symplectic form, I can do it.
Could you explain why this L is locally constant in the space of symplectic form?
Because it's something called generic part. I consider.
No, but why aren't there codimension 1 walls?
No, because I go to complexify the whole thing. It's whole thing analytic. Yeah, so it's the same everywhere, outside of complex codimension 1 divisor, and I can go around it. And so let's explain kind of Leray-Hirsch story first. It's kind of simpler. Cohomology of D is also isomorphic to cohomology of Y plus cohomology of Y shifted by 2 up to shifted by 2n minus 1. And here it's a formula for isomorphism. It's slightly different. Take pullback of homology of Y, multiply by delta, pullback, etc. So I decompose in direct sum. And then if I try to write what is first my grading operator, it's pretty stupid. It's kind of diagonal matrix G plus this matrix. Here's GY, yeah, exactly. It's block n by n matrix. And what is KD? Yeah, it's actually, my notation is not so great because here I mean not canonical class of D, but this operator. But I have still parameters Qt and consider kind of limiting case. limiting case when I put a symplectic form, not really symplectic form, but pullback of symplectic form on y multiplied by infinity. Yeah, so it means that I allow only rational curves which sits on a fiber. These things will be still defined as this limit. And what I get, so I get multiplication by first chain class plus a first quantum correction. The only one term will survive. Quantum correction. It means I consider pairs of points, or 3 points, on sitting in line, sitting in projective space, which is fiber of projection. So usual multiplication corresponds to diagonal, 3 points coincide, and here 3 points lies on a line. And the operator, if we... Sorry? No, it will be first chain class of T star of D will contain T star, because D is bundled on Y. It will still depend on Y. I'll finish the formula. So the operator will be the following. It will be diagonal matrix with multiplication of first chain class of cotangent bundle of Y. It will be diagonal matrix. Then we get another term, minus n times 1, 1, 1, 1, 0, 0. And here we get certain classes called alpha 1, alpha 2, alpha n. Where alpha 1, it will be multiplication by, it will be all linear on a over a ring of cohomology ring of Y. It will be minus first chain class of normal bundle of normal bundle to Y. Alpha 2 will be chunk square C1 square minus C2 and so on. Some kind of expression in characteristic classes. But the important thing is it belongs to cohomology with positive degree. Only, and finally the final quantum correction coming from these lines will be minus n, and you get matrix 1 on the top corner. Yeah, so what is the spectrum? It's all...
Why is there no interesting quantum product by quantum classes?
No, because you treat only curves which are sits in the fiber,
Yes.
and then you get...
Your deformation theory needs to take into account the normal bundle.
Sorry?
For the deformation theory, the curves in the fiber.
Yeah?
Yeah, but it's all of minus 1, so on the lines.
Yeah, so all the rest they don't contribute to the limit. Everything dies. And now it's all operator which H cohomology of Y linear, which is kind of a nilpotent ring, yeah, Artinian ring. But we treat one interesting eigenvalues over complex numbers. And now we can kind of filter by degree of cohomology, in forgetting these shifts. And these things will be kind of upper triangle things. We kind of disappear. And associated gradient, we get just very stupid matrix. You get minus n 1, 1, 1, 1, 1 as a spectrum. And what you get as a spectrum, you get, sorry? Cyclic permutation, yeah, exactly. And you get n times minus n times nth root of 1. Copy, and at each point, at each things, so it will be limit of my connection, and each in semi-orthogonal decomposition, each piece you get copy of cohomology of Y. And yeah, that's how things looks in case of Lehrer-Hirsch. Yeah, I think maybe I need something like 5 minutes. Yeah. And for blow up, the story is a little bit more complication. Then I get cohomology of x tilde, I recall it's a more cohomology of x plus sum of n plus 1 copies of cohomology of y. And then the matrix which you get will be like this. It will be a restriction from cohomology of X to cohomology of Y. And then you get, again, cyclic permutation. So it doesn't contribute to spectrum. And what you get cohomology of X, it's at 0.
Which matrix is this?
It's a quantum product. And I consider, again, kind of forget about things which raise degree in cohomology. So you get H0 sitting in center, and then you get regular polygon of smaller size. It will be minus n minus 1 and minus 1 root of 1, which you get copies of cohomology of Y. Yeah, so you get this things. Yeah, so yeah, I said that it's either proven or should be proven or almost proven, but it's kind of true, clear why it should be true. There are many heuristics. For example, it's if one can argue that one should prove that Foucault categories of X tilde is actually direct sum of Foucault category of X and many copies of Foucault category in Y in this limited. And then, but parameters of Foucault categories are identified by some tricky nonlinear map. So it should be certain identity relating Gromov-Witten invariants of X tilde, and things glued from this story by some relative Gromov-Witten invariants. Yeah, so it will be some kind of nonlinear change of variables, which is very common in the subject. There are many, many examples of this, but unfortunately, as I understand, for example, this story was proven for blow-ups at complete intersections. Yeah, which is stupid. It should be for blow-up, just I think for notational reasons. Yeah. Okay, and then so you see that there are elementary pieces when you blow up.